So welcome to Chapter 2 of the Top-Down Network Design book. This is Analyzing Technical Goals and Trade-Offs. Alright, so technical goals normally are Scalability, Availability, Performance, Security, Manageability, Usability, Adaptability, and Affordability. So scalability is how much growth a network design must support. Availability is the amount of time the network is available to users, often expressed as a percentage of uptime, or as a mean time between failure, also known as MTBF, as well as the mean time to repair, MTTR. Availability goals can be documented in any monetary cost associated with cost or network downtime. So there, the cost of the network downtime can be presented for an availability goal. Security is the goals of protection, the organization's ability to conduct business without interference from intruders, inappropriately access or damaged equipment, data, or operational security all falls in those same categories. Specific security risks should be documented. That way they can be mitigated at a later time. Manageability is a goal for faults, configurations, accountability, performance, and security, also known as FCAPS. Usability deals with the goals regarding the ease with which the network users can access the network and its services and resources, including goals for simplifying user tasks related to the network addressing, naming, and resource discovery. Adaptability is the ease in which the network design can adapt to network faults, changing traffic patterns, additional businesses or technical requirements, new business practices, and other changes. And lastly is affordability, and that is the importance of containing the cost associated with purchasing and operating networking equipment and services, as well as resources. So normally we talk technical goals in form of these items. They are specifically defined so that our network can grow. But you'll notice that flexibility is not here, even if it was an underlying theme. Alright, so moving forward, scalability. It refers to the ability to grow. Some technologies are more scalable than others. For example, a flat network design, it doesn't grow very well. It doesn't scale very well. Meaning, long term, it's not there. So, when we work on scalability, we're trying to learn maybe the number of sites that should be added. Maybe look at past growth patterns. Maybe look at what's being discussed for growth for the next year or two. We're also looking at what the needs for each of the individual sites will be, again, now and in the future. Maybe how many users are expected to be added over the next year or so. How many more nodes, devices, pieces of equipment, servers may be added. All of this is important because this all can tie into growth patterns and making our network flexible enough so that it grows as our needs grow. Availability, normally expressed as a percentage of uptime per year, month, week, day, hour, minutes, seconds, all depending. You have to think that availability for resources normally are focusing on how often are they up. For example, 24/7 operations. Network is up for 165 hours in the 168 work week. Or maybe availability is presented at a percentage. Availability currently sits at 98.21%. Different applications, different requirements, different specifications require different levels of availability. A lot of enterprises may want what they refer to as 5 nines, That means uptime is 99.9999%. And that is of time during the work week. A nice breakdown is, if we're looking at 5 nines, we are looking at downtime in minutes. That's 5 minutes per year. If we are looking at 99.98, we're looking at 105 minutes per year. 99.95, 263 minutes. You see how, even though it's 99% uptime, that 99 point, the digits after the decimal, kind of make a huge difference. Because 99.7, that's 1,577 minutes. That's a lot. That's a total of 26 hours. But at the same token, those 5 nines are kind of expensive. They require a lot of redundancy built into the network. And that means more costs. But if your business is making the money, and for example, we took care of a payday loan company, and they calculated that every 5 minutes they were down, they were losing about $50,000. However, for a network upgrade, it would cost $30,000. But if that new equipment mitigated one downtime, it paid for itself. So the 999999 availability may require things like triple redundancy for ISPs, meaning if one went out, if the second ISP went out, you'd still have a third ISP to allow for communication. Again, it just kind of depends on the organization. But again, can you afford this? But because of the multiple ISPs, you may have things like addressing issues, autonomous system issues. What about ISPs? Are they separate ISPs? Are those ISPs really using one of their peers for transmitting the data? What about routing protocols? So this adds a whole new level of complexity to all of this. So sometimes redundancy comes with its own issues. So availability can also be expressed as the MTBF and MTTR. And that means the availability should equal the mean time between failure divided by the mean time between failure plus the mean time to repair. So for example, the network should not fail more than once every 4,000 hours, or 166 days, and should be fixed within 1 hour. That will allow you a availability time of 99.98. Network performance. This can be characterized in several different ways. This could be characterized as bandwidth, throughput, utilization, bandwidth utilization, offered load versus overload, accuracy, efficiency, delay or latency, or delay variation, and could also be a response time. So, bandwidth versus throughput. Is there a difference? Bandwidth and throughput are not the same thing. Bandwidth is the data carrying capacity of a circuit, where throughput is the quantity of error-free data transmitted per time of unit. So throughput normally measured in bits per second, bytes per second, or packets per second. So again, bandwidth may be the theoretical maximum. Throughput is the actual amount of data going through them. And here is our bandwidth throughput versus load diagram. So our capacity, our throughput, versus our ideal and actual. Other factors that affect throughput could be the size of the actual packet. Are we talking about a regular size 15 byte packet or 1500 byte packet? Are we talking about a jumbo packet? Are we talking about interframe gaps between packets? Could be talking about the PPPS, the packets per second rating of the devices, and how fast the devices can forward those packets. The load of the devices could be also the design, protocols, distance, errors, time of day, ISP, weather, so forth. All of these factors affect the throughput. Throughput versus goodput. Goodput you don't normally hear often, but it does exist. You need to decide what you mean by throughput. Are you referring to the bytes per second, regardless of whether the bytes are user data bytes or packet header bytes? Or are you concerned with application layer throughput? That's the throughput of the user bytes, normally called the goodputs. Meaning, if we're looking at the data going through our network, are we looking at the entire packet? Are we looking at just the user datagram? Or the data portion of the datagram? Or are we talking about the datagram as a whole, including the overhead packet information? All of that comes into play. Throughput versus goodput. Performance or efficiency. How much overhead is required to deliver a specific amount of data? How large should a packet be? How large can it be? How large could it be before there could be data loss? How many packets can be sent in one bunch without any type of acknowledgement, assuming we're using connection-oriented communication, or TCP? So efficiency. If we have several small frames versus several large frames are more efficient, less overhead. However, if a large frame does need to be resent, that's a large amount of data. So what about the delay from the user's point of view? The response time. And this is a function of the application and the equipment that the application is running on, not just the network. We're looking at that the average user is expecting to see something on the screen within 100 or 200 milliseconds. We live in an age of right now, so if it's taking too long, even just half a second, it's showing that the response time is not adequate. Delay from the engineer's point of view, and that's going to be the propagation of delay, and that's going to be the signal traveling in a cable is about 2/3 the speed of light in a vacuum, meaning transmission delay, also known as serialization delay, is the time to put a digital data onto a transmission line, meaning, for an example, we're looking at takes about 5 milliseconds to output a 1024 byte packet onto a T1 line. Other forms of delay from the engineer's point of view could be packet switching delay or even querying delay. So querying delay and bandwidth utilization, as we see that as the average utilization goes up, so does the average query depth. Examples. A packet switch has 5 users, each offering a packet at a rate of 10 packets per second. The average length of the packet is 1024 bits. The packet switch needs to transmit this data over a 56K WAN circuit. So that means our load is we have 5 users at 10 packets per second. Each packet is about 1024 bits. So we are looking at 51,200 bits per second. Utilization is going to be our load divided by the transmission bandwidth. So here we have our 51,200 divided by our 56K circuit. So that's going to mean we have about an average of 91.4%. So that means the average number of packets in queue is around about 10.63 packets. Delay variation. This is the amount of time delay varied. This could also be known as jitter. This is important when we talk about things like voice, video, audio, because all of these are intolerant to delay. They all have a real-time component. And that's the issue. So forget everything we've said about maximizing packet size, because at this point, our delay is an issue. Security. And normally the focus on requirement first. We're going to talk more about this in Chapter 8. But we need to identify network assets and their values and analyze the appropriate security risks. That way we know how to prioritize our traffic. We may need to know that we have to prioritize HR traffic over everyone else, or quality of service for voice or video above everything else. You're going to have to do some type of risk analysis to figure this out. Network assets. They can include things from like hardware, software, applications, data. Data could include things like intellectual property, trade secrets. Could also be things like reputation. Network assets could be lots of network resources. So do keep that in mind. Security risks. Hacked network devices is a normal risk. Data can be intercepted, analyzed, altered, or deleted in transit. Things like user passwords could be compromised. Reconnaissance of an attack, or even things like denial of service. All of these are huge security risks. So we have to be implementing some type of security measures to mitigate these risks. Manageability. Things like managing the fault tolerance of the network, managing the configuration, the accountability, the performance, and the security. All of those focus on the manageability of the overall network. Usability. Again, usability is the ease at which we can use the resources. Networks should make users' job easier, not more complicated. Some design decisions will have a negative effect on usability. For example, strict security makes it harder for the users to use it. Adaptability. Avoid incorporating any design elements that would make it hard to implement new technologies for the future. That's pretty straightforward. We need to keep a more fluid, flexible design so that we can adapt to changing. That's changes in technology, that's changing in traffic patterns, and that's also could be changing for quality of service. Adaptability and flexibility are huge because, again, our network is going to be fluid. It's going to change as our requirements change. Affordability. The network should carry the maximum amount of traffic possible for a given financial cost. All of this equipment is going to cost something. So we have to have the appropriate type of design where we're going to have the most bandwidth, most resource availability, most things for our money. And affordability is especially important when we start talking about campus area network designs, CANs. Same thing with WANs, because WANs are expected to cost more, but costs can be reduced based off of the proper use of technology. WANs are separate from CANs, which are separate from LANs, and they're all going to have their unique characteristics. Network application technical requirements. Here's a great little flowchart. So we can actually do the, we rank them, name of application, cost of downtime, the acceptable MTBF, the acceptable MTBR, throughput, delay, variation. That way we can start ranking our different applications and our different technical requirements. That way we have a better way to categorize our overall strategy for the network. For example, making trade-offs. If scalability is going to be 20% of our focus and availability is going to be 30% of our focus, network performance 15, security 5, the rest of them all 5, we can make trade-offs. That way security may be increased, but that means we're going to have to lower the rank of another item. For example, if security is a huge, but scalability is not that important, we may lower scalability down to 15 and increase security up to 10. So again, this is all making the trade-offs for your specific situation. So in summary, we're going to continue to use a systematic top-down approach. We're not going to select products. Our goal here is to understand things like scalability, availability, performance, security, manageability, usability, adaptability, and affordability. Trade-offs are almost always necessary as an end result. We're not going to have unlimited resources, so we have to be able to spend more wisely. I want to end you guys with some review questions and thoughts. So, first review question. What are some typical technical goals for organizations today? How much bandwidth and throughput differ? How can one improve network efficiency? And what trade-offs may be necessary in order to improve network efficiency? That's all I have for Chapter 2. Thank you.